Pluto, a distant and enigmatic celestial body, has long captured the fascination of scientists and space enthusiasts alike. Once regarded as the ninth planet of our solar system, its reclassification as a dwarf planet sparked debate. Now, recent remarks from prominent astrophysicists like Neil deGrasse Tyson and Michio Kaku have once again thrust Pluto into the public spotlight. These experts have raised startling concerns about the possibility of Pluto's trajectory bringing it dangerously close to Neptune, a scenario that has sparked widespread curiosity and even concern. But how could such a catastrophic event unfold? What would the potential consequences be? Is this merely a rare cosmic anomaly, or could there be deeper forces at play that we have yet to fully understand? Join us as we dive into the science behind Pluto's orbit and explore the real possibility of a collision with Neptune. Pluto's status as a planet was revoked in 2006 when the International Astronomical Union redefined what it means to be a planet. Its unusual orbit was a key factor in this decision. Unlike the near-circular orbits of the major planets, Pluto follows an eccentric and inclined path around the Sun, making its movement highly unpredictable over long periods. Despite being reclassified as a dwarf planet, Pluto remains a subject of intense study, and recent research suggests its trajectory brings it uncomfortably close to Neptune's orbit. Astrophysicists like Tyson and Kaku have sounded the alarm over a potential catastrophic collision, theorizing that Pluto's orbit might one day intersect Neptune's. While such an event would be unprecedented in modern astronomical history, understanding the mechanics of this possibility requires delving deeper into the physics governing planetary motion. Unlike any other planet in our solar system, Pluto's journey around the Sun is extraordinarily slow and erratic. It takes 248 Earth years to complete just one orbit, meaning that since its discovery in 1930, Pluto has yet to complete a full trip around the Sun. This prolonged orbit contributes to the mystery surrounding its trajectory. But the strangeness doesn't stop there. Pluto's path is highly elliptical, deviating significantly from the nearly circular orbits of most other planets. To complicate matters further, Pluto's orbit is tilted at a steep 17-degree angle relative to the plane of the solar system. This inclination makes its movement more extreme compared to other celestial bodies, adding layers of complexity to predictions about its long-term stability. However, one of the most intriguing aspects of Pluto's orbit is its periodic close approach to Neptune. For approximately 20 years of each orbit, Pluto actually moves closer to the Sun than Neptune does. This counterintuitive positioning naturally raises the question, if their orbits cross, why haven't Pluto and Neptune collided? The answer lies in the delicate balance of gravitational forces governing planetary motion. The gravitational influence of other massive planets, particularly Jupiter and Saturn, plays a crucial role in stabilizing Pluto's orbit. Additionally, the phenomenon of orbital resonance ensures that when Pluto reaches the point where its orbit crosses Neptune's, the two bodies are always positioned at safe distances from one another. This is due to a 3-to-2 resonance, meaning Pluto completes 2 orbits around the Sun for every 3 orbits Neptune completes, preventing direct encounters. Another important concept is vertical libration, which describes Pluto's vertical movement in relation to the solar system's plane. When Pluto nears Neptune's orbit, it is positioned either above or below Neptune's path, further reducing the chances of a collision. This intricate gravitational dance has kept Pluto's trajectory stable for billions of years. Even more fascinating is the concept of VZK wobbling, named after researchers who studied how celestial bodies influence one another through gravity. This phenomenon explains how the gravitational pulls of Pluto, Neptune, and the Sun interact to keep Pluto's orbit in check, despite its apparent irregularities. While Pluto's movement may seem chaotic at first glance, these subtle but powerful forces help maintain order in the solar system. However, planetary orbits are not set in stone. Over long timescales, even minuscule gravitational interactions can accumulate, leading to potential instabilities. The three-body problem, a fundamental challenge in celestial mechanics, describes the unpredictable interactions between three gravitationally bound objects. In Pluto's case, the Sun, Neptune, and even Jupiter's immense gravity contribute to its long-term orbital evolution. Simulations run by astronomers have provided insight into Pluto's long-term trajectory. These complex models use advanced mathematical equations to simulate how Pluto, and other celestial bodies interact over millions or even billions of years. Researchers have found that while Pluto's orbit remains relatively stable today, small perturbations could eventually lead to dramatic changes in its path. This means that while a Pluto-Neptune collision is not imminent, the possibility cannot be ruled out entirely over extremely long timescales. Jupiter's gravity, in particular, exerts a stabilizing influence on Pluto, ensuring that its orbit does not deviate unpredictably. Combined with the forces of Saturn and Neptune, these interactions create a delicate equilibrium that has kept Pluto on its current course. Without these stabilizing forces, our solar system could be far more chaotic, with planets and dwarf planets colliding or being ejected into deep space. Even the slightest alteration in Pluto's speed or position could trigger long-term changes in its orbit. This sensitivity to initial conditions makes predicting celestial events incredibly challenging. Any errors in initial measurements can lead to vastly different outcomes, making long-term orbital forecasts uncertain. Despite its apparent chaos, Pluto's orbit has remained stable for billions of years, demonstrating the hidden order within seemingly unpredictable celestial mechanics. The unpredictable nature of these systems serves as a reminder of the complexities of our universe and the vast unknowns still waiting to be explored. Neil deGrasse Tyson, known for his advocacy in reclassifying Pluto as a dwarf planet, argues that this shift reflects our evolving understanding of the solar system. He sees Pluto's erratic orbit not as a flaw, but as a testament to the complexity of celestial mechanics. His perspective highlights the importance of continuous learning in astronomy and planetary science. Michio Kaku, another leading physicist, echoes these sentiments while also raising concerns about Pluto's long-term future. He suggests that while Pluto's orbit appears stable today, gravitational interactions with other celestial bodies will continue to shape its trajectory. Additionally, the eventual transformation of the Sun into a red giant and its subsequent collapse into a white dwarf could alter the solar system's gravitational structure, potentially affecting Pluto's path in unpredictable ways. While the likelihood of a Pluto-Neptune collision in the near future is extremely low, the uncertainties of celestial mechanics remind us of the ever-changing nature of the cosmos. Even small gravitational perturbations can accumulate over vast timescales, potentially leading to major orbital shifts for distant objects like Pluto. The study of Pluto and other celestial bodies continues to challenge our understanding of planetary dynamics, gravitational interactions, and the fundamental principles that govern our universe. As we develop more advanced tools for space exploration and more sophisticated simulations of orbital mechanics, we may one day unlock even greater mysteries about Pluto's ultimate fate. For now, the possibility of a catastrophic encounter with Neptune remains an intriguing, albeit distant, question, one that highlights both the beauty and unpredictability of the cosmos.